Welcome to this video lesson on the basics of velocity vectors. Prior knowledge for this video include geometric and algebraic operations, magnitude of a vector, and displacement vectors. Velocity is a concept that is discussed in calculus in a lot more detail, but by definition is the rate of change of displacement with respect to time. It gives us two very important information. One is how fast an object is moving, usually measured in units of meters per second or kilometers per hour, and that's the speed of the object, and its direction. And direction could be as simple as right, left, up, down, or north 25 degrees west, which is 25 degrees west of north. With vectors, we often deal with average velocity and not instantaneous velocities. For average velocity, it's defined as the displacement over the amount of time, and we use delta d to represent the displacement vector and delta t to represent the change in time. And this can be rearranged for delta d, and that will equal to the average velocity multiplied by the change in time. Now, average velocity is a vector quantity, so it will have x and y components and sometimes a z component if it is in 3 dimensions. We can find the magnitude of the average velocity by the root of x squared plus y squared components of it, and this is Pythagorean theorem, and we can find the angle by using SOHCAHTOA, or just tan inverse of the opposite over the adjacent side. For basic vector questions, we often use river-type problems or plane-type questions. So let's look at an example. We get a river which is 4 kilometers wide and flows at a rate of 10 kilometers per hour. We get a boat that travels at 20 kilometers per hour, steering perpendicular to the current. A marina is directly across a bank on the opposite bank. And we want to see how long it will take for the boat ride to take and how far downstream from the marina will the boat reach. And downstream means the distance in the direction of the flow. There's a lot going on, so we're going to draw this situation out. We got a river which is 4 kilometers wide. We got a flow in one direction. It could be right or left. It really doesn't matter. We got the boat coming down perpendicular at velocity of 20 kilometers per hour, and the river will take it with a component of 10 kilometers per hour in the direction of the flow. And the marina is right opposite to it, and it's going to land downstream somewhere in the direction of the flow compared to the marina. For the first part of the question, we're only looking to see how long it took, and we already have 4 kilometers in the y direction, and we know the speed in the y direction as well, and that's all we really need to solve this. So for part A, we're going to let down to be positive, and we're going to write that the average velocity in the y direction is its displacement over the change in time. Rearrange for delta t to get displacement over the average velocity. Since we took down to be positive and it traveled downwards, we're going to put positive 4 divided by 20 because it's going down. It's also positive, and that gives us 0.2 hours. For part B of the question, we want to see how far in the direction of the flow the boat travels. So we only care about the x direction and not the y direction anymore. So in the x direction, we're going to take right to be positive. The average velocity is displacement over time. Rearrange it for displacement to get Vx times delta t. And the velocity in that direction is 10, and the time we already know is 0.2 hours. And when we multiply that, we get 2 kilometers. And since we took right to be positive and our answer was positive, then and that's to the right, which is the direction of the flow. Now let's look at plane problems. So with planes, we usually have the plane which is traveling with a certain speed, and we got the wind which is traveling in certain speeds, and their combination is the velocity that we see the plane from the ground. So if we're standing on the ground and looking at the plane, we see it traveling at velocity vg. So that's the velocity of the plane relative to the ground, and that's equal to the velocity of the plane plus the velocity of the wind. Sometimes we use this in boats as well. So the velocity of the boat relative to the ground is equal to the velocity of the boat plus the velocity of the currents. Let's look at a quick example here. We got a plane which is traveling at a speed of 400 kilometers per hour northwest, and we got a wind that's coming from the west with a speed of 50 kilometers per hour. It's a good idea to draw these out. We're going to take east and north to be positive here. Then we're going to start drawing our 400 kilometers per hour, which is the speed of the plane, and that's at a 45 degrees north of east or east of north. And then we know the wind is coming from the west, so it's moving towards the east, and that's 50 kilometers per hour. And the resultant velocity is the ground speed, which is going to originate from the tail to the head of the final vector. So we have an angle from the east to our final vector, and we got an x and y component to that vector as well. We can find the ground velocity by adding the plane velocity to the wind velocity, and what we do is we take their x components, add them together to get the x components, and we add the y components to get the y components of the ground velocity. Or one other method of doing this is the cosine rule, and we can use the cosine rule to find the magnitude of the velocity or ground velocity and the angle as well. Here's a summary to the concepts from this lesson. If you want to write any of them down, please feel free to pause the video. And now we're going to look at an example. Okay, in our example, we got a boat that heads 10 degrees west of north with water speed of 5 meters per second. Determine its velocity relative to the ground when there is a 3 meters per second current from 50 degrees east of north. Let's start drawing this out. So for our velocity of the boat, it's going 10 degrees west of north, so we'll draw north and we'll draw a vector which has a magnitude of 5, and that's going towards west, and that will have its x and y components. The wind has a speed of 3 meters per second from 50 degrees east of north, so we'll draw a coordinate system labeled east and north, and 50 degrees north of east is using a dash line, and it's going towards the opposite direction, so we'll label that and we'll give it a magnitude of 3, and we'll have the angle there as well. And we know that this will have an x component and a y component. Let's combine them for a mental image. We have the first vector, which is VB, added to V current and originated from the tail to the head of the final vector, and VG should be going in this general direction. We're going to choose a positive coordinate system, and we're going to take north and east to be positive. And for the boat, the x component is going in the left direction, which is opposite to the direction that we have chosen. So that's -5, and since it's opposite to the angle, it's sine 10. And for the y component, it's going in the same direction as our coordinate system, and since it's the adjacent side, is 5 cosine 10. For the current, the x component is going opposite to our coordinate system, and therefore it's a -5, and since it's opposite to the angle, it's -5 sine 50, and the y coordinate is also opposite to our coordinate system, so that's -3 cos 50. For the ground speed, we are going to add the two vectors, so we're going to add their x components together, and we're going to add their y components together. We're going to get approximately negative 3.2 for the x component and 3.0 for the y component. Now we can draw these components out. So for the x component is going opposite to our coordinate system, so it's going to the left, and for the y component is going the same direction, so that's going up. Our resultant vector originates from the tail of the first to the head of the last, and the angle in between is shown. To find the magnitude, we will use Pythagorean theorem, so it's the root of the x component squared plus y component squared to give us approximately 4.36 kilometers per hour. And since we have the opposite and adjacent to the angle, we know that theta is the tan inverse of 3 divided by 3.2, so it gives us an angle of 43.2 degrees. Putting everything together, the ground velocity is approximately 4.36 kilometers per hour in the direction of the west, and from west is 43.2 degrees towards north, and that is our final answer. Okay, I have prepared 2 questions for you folks to try out, and I will try my best to post the full solutions to this in a separate video. I hope that this video was helpful in giving you some idea about the basics of velocity vectors. Thank you for watching.